Hi, this is a quick video to show how you can use the TINC client in Python to interact with the C++ application, to inject computation into the application and to configure its behavior and to find out the data set and the state of the application. We're going to be using Chasm Viewer, which is a C++ application that we've developed together with the Van der Ven research group here at UCSB. So this is an application that displays data sets from the Chasm simulations showing how atoms are filling vacancies in a lattice. So I'm going to prepare the importing of TINC. We're going to be using TINC version 0.9. So it's an early version, so API might change. So we create a TINC client object to connect to the C++ application, and you can see that we are now connected. We're going to access parameters first. These are the parameters that have been made available by C++ to the TINC client. And we can get a particular one here, for example, time. And we can set the value from Python, and you can see that it actually sets it here in C++. You can also do it the other direction. So if we set it here, you can see that the values are kept synchronized in both instances. You can also inject computation that can be triggered from parameter changes. So you can create a function that takes a value, which is the new value of the parameter, and then you can register that to the parameter itself, right? So if I set a new value, right, it triggers this callback and prints the value. It goes again both ways. So if I click it here, the change in C++ will actually trigger the computation in Python. So it doesn't matter where the change has occurred. You can use all of these together with the caching system that TINC makes available both for callbacks and for parameter spaces. You can see that in my other video where I do kind of an introduction to TINC. Parameters can also have more complex data than single float values. For example, Chasm Viewer exposes the color of an atom marker. So if you see here, I'm just going to set this to be a different color, red, right, RGBA, and just make it a little bit larger. So you can see here it's turned red and a little bit larger. Let's make it yellow and a little bit smaller, right? So you have control of all of these things like that, where you can just kind of control the behavior of the application and the current parameters that are being worked on. Sometimes parameters are not enough. Sometimes you want larger data, more complex data to be exchanged between Python and C++. So for this, TINC provides what are called disk buffers. These buffers exchange this data in a seamless and reactive way through a shared file system between this instance and the C++ application. And they handle both the loading, the decoding of data whenever they get a notification that the disk buffer has changed. So I'm going to show two examples of two different types of disk buffers available in TINC, even though there are a few more. So these are the disk buffers that Chasm Viewer is currently making available to TINC. The first group is for graphs. So these are going to be image buffers where we will write a PNG to disk, and then the PNG will be automatically loaded and displayed in a little panel in the C++ application. So I'm going to get that buffer. I'm going to write a little function here to create just a dummy random plot in matplotlib. All you have to do for buffers in general is get the file name that you need to write to, then write to that file name, and finally notify the TINC client that you're done writing. So this is all you have to do on the Python side. So if I write this graph with a value of 15, you will see that it's being displayed here in this panel. This is displaying the disk buffer graph 5. So I can set a different value, right? And you can see that this was actually regenerated in Python and automatically loaded on the C++ side effortlessly. You can also register callbacks that can do this kind of thing. So I'm going to register this one as a callback to the time parameter. So you can see that when I change the time parameter, two Python functions are actually being called, one that generates the graph and one that prints this value. I'm just going to clear them so that we can move forward. The other type of disk buffer that I'm going to show is one that can display a set of markers for vectors. And this disk buffer is called trajectory buffer. There are a few graphical elements in TINC that update automatically from disk buffers. So all I have to do is make a little function that will write in JSON format these positions, which are going to be relative. So this is the start point, and then this is relative to that one, and then this is relative to wherever the previous ones ended. So I just write that as I did before. And when I write to the JSON file, right, you can see the markers being shown here. These graphical classes in C++ also provide to the TINC client configuration options, for example, the width. So you can see I've changed the width of the display here. TINC is also very useful to help you explore data sets. As you're visualizing, you might see something interesting, and then you want to find out where in the data set you are. And sometimes these data sets are kind of spread out across the file system in many directories as a result of, say, parameter sweeps, for example, or across a number of files. So TINC will help you automate these kind of tasks and help you find the files you need across a file system. This is done through the parameter space class. And the CASM viewer has made this parameter space available. So I'm going to get it, and this tells me the root of the parameter space. So this is going to be the root in the file system that holds this parameter space. Then, according to the current values in the parameter space that I'm at, the paths that will be appended will be different, right? So, for example, the 59 comes from the folder I'm at, and the conditions comes from the temperature. Right? So this parameter determines the first component of the folder, and this temperature determines the second component. So the exact file where I'm loading, where the C++ application is loading the data set is this one. You can see that parameter spaces contain parameters, and you can see these three parameters are the ones that are configuring this parameter space. Right? So if I change any of these here in the C++ application, they will also change here in Python. And of course, they will affect the current path I am in. You can also set them from here, right? And you can change them, and the path automatically changes. So TINC becomes a very convenient way of exploring these data sets across multiple directories. Another thing that we found very useful for exploring these data sets is allowing the researcher to create his own or her own custom interfaces. So we're going to create a few parameters here, and you can see that once I run this has created a slider here. So I'm going to create 4 of them, and I'm going to use them to determine which data set to load. So the combinations of these parameters will determine a path that will then request a load from Python to C++. And then, so what I do is I register this function as a callback to any of them. So when any of them changes, this will trigger a load, right? So as I change it here, this will actually trigger, well, this hasn't changed. So let me trigger a load here, for example. So when I do this, this will actually call this function. And right now the data set is loading. It takes a little bit for the data set to complete loading. You can do it again with another value. You can put all of this together, for example, to make a GUI, right? That makes a trigger. Okay, it's still loading. We'll see the trigger button as soon as this is done. And you can write a callback function to that button, and then you can register the callback to this button. Right, you can see it working there, and then this has come up a trigger, and you can see that this callback has been called. So you can put all of these together. You can trigger functionality, make parameters, and explore the data set by kind of injecting Python code into the C++ application. We will have another video that displays the impact that this has had on the science side fairly soon.